Okay, 5.5, exponential and log models, okay? So, highlights here. What are models in the real world that use exponential? So, and log. The main ones are growth models. So growth and decay models are going to be our main models that we use. So notice for growth and decay, the only difference is that your B is positive here and your B is negative here. Okay. The next model is the Gaussian model. Gaussian, I can never say this correctly, but model. And it's pretty much this. It's a little bit of everything. You have squares, you have division, all of your exponent taking place. Okay. And then our next model is our logistics growth model. Logistics growth model is A divided by 1 plus BE to the, I think it's a negative RX. This should be, if you can't see it, it says negative RX, okay? Hopefully that made it a little bigger for you. And then lastly is our log models are y equals A plus B natural log of X and y equals A plus B natural log 10x, so common log x, okay? And so we're going to go through kind of how to recognize the most common uses of these functions, okay? All right, first, exponential growth and decay models. So if you have an exponential growth and decay model, they usually start off with some type of population is growing or declining, right? So it says, suppose the population is growing according to the model, P equals 800 times e to the 500th t, okay? Don't know why there's an extra equal sign there, just ignore it. Where t is given in years. What is the initial size of the population? Okay, so it's asking us to figure out, what's the initial size, and then we're going to figure out how long will it take this population to double. Okay, your initial is always your number in front. This right here, in terms of transformations, it's your A. Okay, in terms of population here, it's also our A. Good. So it's our A value. So our A equals 800. This is our initial. Okay, that's your initial size of your population, 800. Okay, it wants to know how long will it take this population to double. So we want to know how long will it take for P to equal 1600. So we have our P. We have an equation to utilize to set P equal to. So 1600 equals 800 times E to the 500ths times T. And our goal is to get T by itself. So we're going to divide 800. And that's going to give us 2 equals E to the 500ths T. Okay. In our last section, we talked about once your exponential is by itself, you can take the log of both sides. Okay. So the log of both sides would be natural log because we have E. So we're going to take the natural log. And now we're left with the natural log of 2 equals 500ths T. Like that's because inverse property, our E, our natural log cancels out our E. Okay. The last thing we want to do is get T by itself. So we're going to divide by 500ths. Our T is now by itself. So how long is it going to take us? Well, we're going to go to our calculator. In our calculator, we're going to type in natural log of 2 divided by 500ths. And we get about 13.86. So 13.86 years is how long it's going to take for our population to double. Okay, and that's using a growth and decay. All right. So here it says, to estimate the age of dead organic matter, scientists use the carbon dating model. What is the carbon dating model, you ask? I'm so glad you asked. It is R equals, how can I write this in one line? We're just going to do it very carefully. 1/10 to the 12th times E to the negative T divided by 8,245, okay? Which denotes the ratio R of carbon-14 to carbon-12 present at any time in T, okay? So let's see. When is this applied? To fossils, okay? So the ratio of carbon 14 to carbon 12 in a fossil is R equals 10 to the 16. Okay, so we now know our R value. It says R equals 10 to the 16. So we have 10 to the 16 equals, and I'm going to write it 1 over 10 to the 12 times E, and it is negative T over 8,245. So some really smart person figured out how to estimate the age of things that have been gone for a very long time. All right, so the goal here is to get to T. That's what we want. Before we can get to T, we got to get rid of 1 divided by 10 to the 12. Well, if I'm dividing by 10 to the 12, that means I'm going to multiply it by 10 to the 12. And what I do to one side, I'm going to do to the other side, okay? So this cancels. Exponent rules. When you're multiplying exponents with the same base, that means you're adding your power. So this becomes 10 to the 28 equals E to the negative T divided by 8,245. Okay, you want to keep exact values as long as possible. So do not feel like you need to put 10 to the 12 in the calculator yet. You want to keep it going until the very end. Okay. Uh-oh. I messed up. You can't see it. And I couldn't see it until this is supposed to be 10 to the negative 16. That's what was missing. I was like, what is that space? It's 10 to the negative 16. So 12 minus 16 is negative 4. There we go. A little fix. No biggie. So we have 10 to the negative 4. All right, we're going to keep going. Now we have E. And so with E, in order to cancel out E, we have to take the natural log. Okay, because we're getting used to this, I'm going to just kind of squeeze it in there. The natural log is going to cancel out E, and I'm going to be left with the natural log of 10 to the negative 4 equals negative T divided by 8,245. Okay, because I'm dividing 8,245, and because this is negative, I'm just going to go ahead and multiply by negative 8,245. What that's going to do is going to cancel out my negative and cancel out this. So, but what I do to one side, I have to do to the other side. Okay, so now I know the exact value of T. T equals negative 8,245 times the natural log to the negative 4. So I'm going to go to the calculator. I'm going to put that in there. So we have negative 8,245 times the natural log of 10 to the negative 4. This is my exact value. It's going to spit out an approximate age of my fossil. So approximately my fossil is 75,939 years old. So we get 75,939 years old. All right. Okay. Okay. Our next model that we're going to look at is the Gaussian models. And so Gaussian model is commonly used in probability and statistics to represent populations that are normally distributed, is what we're putting here. So we're writing normally distributed. I feel like I'm spelling that right, y'all. There we go. Okay. And it's usually modeled on a bell-shaped curve. The average value for a population is where the maximum Y value is. Okay, so for our Gaussian models, remember that's the Y equals A times E to the negative X. I'm trying to remember it all. X minus B squared divided by C. Yeah, there we go. My E looks so tiny. Let me fix that for you. Ew. All right. And so how does that look? We're going to draw the basic form of the graph, and I'm going to draw it, and then I'm also going to Google it so that you can see a better a better representation of a Gaussian model than what Miss Jones is drawing. Because as you know, my drawings are not the best, but I try to make them. I'm actually going to give myself a little pat on the back because I feel like that's a fairly good bell curve. All right, so really quick, that was me preparing for carbon dating, y'all. We have GAUSAN models. We're gonna hopefully it pulls up a good bell curve. There we go. So as you can see, here's some. So you can see this m squared mean, our average mean is right here. But I was just trying to get you to see that it is a bell curve and it's being equally distributed amongst the curve, okay? If you plan on going into pretty much almost any field that's medical, business, finance, poli-sci, you're gonna probably take a stats class because you have to be able to analyze the data. And so you guys will dive a little deeper into it, but I just wanted you to see what a Gaussian model looks like and highlight the fact that it's going to be your maximum value of that function. So when you're looking at it and you graph it, you're going to look and see, okay, where is the max value taking place at? What is my maximum Y value? Okay, so this is going to be solved more by graphing and analyzing than anything. All right. Next, logistics growth models. So it says, give an example of a real life situation that is modeled by a logistics growth model. I know the only example that I could come up with was a science-based example, and it would be bacteria cultures. So if you have bacteria culture that is initially allowed to grow under ideal key thing here is ideal, because you know in science we only can have so many conditions and parameters that we can control conditions, and then under less favorable ones you can compare the two. So under less favorable conditions that inhibit it from growing. That's really inhibit, right? Feels wrong, but hopefully it's right. That inhibit the growth. You can then compare the two models and examine what it looks like. Okay. The basic model that we're looking at when you have a logistics growth model is kind of like a sideways wave. Again, pretend that these are the straightest lines you've ever seen, okay? It's gonna typically always be positive, so you're not looking at negative y's, and it's like a wormish sitch. Okay, it's looking something like this. Again, we're gonna go to the internet, and I want you to see a better version of the model than mine. So we're gonna do a logistics growth model. So you see what I was saying, like it's kind of like a wormish curve situation that's taking place. Okay. With logistics growth, it's usually over time, population, and there's a capacity that takes place. Okay. So the difference here is you can see the exponential growth model, there's no capacity. But with our logistics growth model, you're saying, okay, where am I going to stop? Where's my limit exist at? Okay. All right. So that's our next type of example. And again, you'll further dive into that if you are doing statistics for our class and for what's needed for our course. Just being able to see it and analyze it is good enough. Next, we have our logarithmic models. So our log models, have no clue what happened to my wording here, but it should be, here it says the number of kitchen widgets, Y in millions demanded each year is given by the model. Y, I'm going to rewrite it. Y equals 2 plus 3 natural log of x plus 1. Okay. And here it's saying where x equals 0. Okay. Represents your initial year. So year 2000 is our 0 value. Okay. And so from then on, x just goes up from there, right? It's just increasing. That's what it says. So it says find the year in which the number of kitchen gadgets demand will be 8.6 million. Okay. So it's looking for 8.6 millions. And again, this is already in millions. So you're not writing in 8,60000. I think that was 5. So we are trying to figure out how long would it take. Okay. And again, x represents the years after. So therefore, the 8.6, that's our y. So if y equals 8.6, right? Well, we already know what y equals. So we have 2 plus 3 natural log of x plus 1. And our goal here is to get our natural log by itself to solve. So in order to do that, the first thing I'm going to do is subtract 2 from both sides. That's going to leave me with 4.6 equals 3 times the natural log of x plus 1. I'm not completely by myself, so I'm going to have to divide by 3. And again, I want to hold on to those values for as long as possible, so do not put anything in the calculator yet. So we're left with 4.6 divided by 3 equals the natural log of x plus 1. After we have the natural log, the only way to get rid of the inverse operation of natural log is exponential. So we're going to raise both sides to the e. By doing this, it cancels out e to the natural log. So we're left with e to the 4.6 divided by 3 equals x plus 1. The last thing we need to do to get our x by itself is to subtract 1 from both sides. So we subtract 1, and therefore, final answer, x equals e to the 4.6 divided by 3 minus 1. Okay, this is my exact value. I'm not going to tell someone in approximately e to the 4.6 divided by 3 minus 1 years, you will have 8.6 million kitchen gadgets. No, I'm going to go to the calculator and input that. So putting into the calculator, I have second e. Probably should go down. I have second e, and I have 4 6/10 divided by 3, arrow out of the exponent, out of the power, minus 1. I hit enter, and I get approximately 3. I got 3.6. Okay, so we get 3.6. So x equals about 3.6 years. So what's the year that would be? So 2000 plus 3.6 would put me at about 2003 plus years. Okay. All right. And so that's how our model works. All right. Hopefully we feel okay about this. And if we have any questions, comments, concerns, oh guys, I made a huge mistake in math and no one was here to talk to me about it. 8 minus 2 is 6. Ha! Found it myself. 8 minus 2 is 6. And we're gonna fix that. And I was like, that is not right. I got 2000 in my notes and I don't know why, but I know why. So we're gonna fix this little boo-boo. And we're going to pretend that we never saw it. All right, erase, 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 erase. And as you were doing this, you're probably like, Miss Jones, what are you doing? And I'm like, I don't know, guys. I don't know. So I'm going to erase, 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 and fix myself. I'm so sorry. 8 minus 2 is 6, in case you didn't know. So everywhere that there should be a 6, I'm going to put the 6. Okay, so in the calculator, I'm actually putting e to the 6.6. So I'm going to arrow up. What this allows me to do and hit enter, it allows me to fix my error. So I'm going to go over, and I'm going to put 6 and hit enter. This is more right. And so I get 8. So once I fix my 6, I'm at 8.03 years. So just basically 2000 plus 8 is 2008 years. Okay. Again, Lo siento, y'all. I don't know how I did that, but luckily I caught it. All right. That's it. That's it for Unit 5.